Hey everyone, Mr. Fransky here. One more video about an AP review problem here. It's going to be area, volume, and length in this one. They don't always ask a question about something like this on the BC test, but every once in a while it does come up, so I want to make sure that we cover one of these. It's always on the AB test, though. So let's take a look. So this is our topic list for Chapter 7. Rate in, rate out is in a different video, motions in a different video. This is going to kind of cover all of these. Okay, so area between curves, volume using similar cross sections, volume of revolution using disks and washers, and volume of revolution using shells. It's really the last two. If you wanted to create a problem using similar cross sections or find the area in this problem, you definitely could. I'm also going to cover length of a curve in this one. Alright, so it's a no calculator problem. F of x is e to the 2x, all right? That's our curve right here. R is the region in the first quadrant bounded by the graph of f, the coordinate axes, and the line x equals k, where k is a positive number. Interesting. The region R is shown in the figure above. Okay. First, write but do not evaluate an expression involving an integral that gives perimeter. So I have to find the perimeter of it. Then we're going to rotate it around the x-axis and find the volume. Then they kind of sneak a related rates problem in here. So the volume v found in part B changes as k changes. Indeed, if k gets bigger, the volume is going to increase. If k gets smaller, the volume decreases. So if k is increasing at 1/3, determine how the volume is changing when k equals 1/2. So I gave this one as an entire problem because I thought maybe you want to try it on your own first. I also added 4 more because I can. These are some are going to be shell problems. I also added one where you're revolving around a line above the function, one to the right, one to the left, and one below. Actually, I don't think I did it below, but I did it above. So if you want to try this on your own, you can. Then come back and we'll talk through it. So the first 3 problems are the only parts that would be on the AP test. So hopefully we'll be able to get those done in less than 15 minutes because that's the goal for the AP problems. But then the last ones we'll kind of do just because I want to make sure that we have kind of shell method down on this as well. All right, so let's jump in. So first, write but do not evaluate an expression involving an integral that gives perimeter of r. So they don't ask for the area in this, but you would just integrate underneath the function from 0 to k, right? Not too bad. So this time they want us to give the perimeter. So the perimeter of this consists of 4 segments. 1, 2, 3, and then the function up here. So let's do the easy ones first, right? This guy right over here has a height of 1. You can double check that by plugging 0 into the function. E to the 0 is equal to 1, so that's definitely going to be 1. Plus the length along the bottom. Well, the length along the bottom goes from 0 to k, so k. And then at k here, the height of this line is going to be the function value at k, which is e to the 2k. They even gave it to you. Okay, and then we have to add to that the length of the curve right here. So remember, curve length, integral from a to b, square root 1 plus the derivative squared, dx. Okay, so the derivative of e to the 2x. So if f of x equals e to the 2x, then the derivative is going to be leave it alone, and then multiply by the derivative of the baby function, which is 2. So 2e to the 2x. So what we have here is the integral from 0 to k, square root of 1 plus 2e to the 2x squared, dx. That should be the perimeter. Okay. Big trap to fall into here is just giving the curve length, right? Remember, they want for the perimeter, so you have to give all 4 pieces of it. Let's see how we did. 1 plus k, e to the 2k, and then integral from 0 to k, 1 plus 2 e to the 2x squared dx. 1 point for getting the derivative correct, so make sure you're writing down all your work. 1 point for having the integral correct, and then 1 point for the entire answer, so that's making sure you get all those pieces together. 3 out of 3. Cool, let's move on. Next, the region is rotated around the x-axis. Okay, to form a solid. Find the volume of the solid in terms of k. So let's kind of see what that's going to look like. So kind of a curve like that, and then there's our k line. So we're going to have disks here. The one time that they ever give you disks. But I mentioned in class that when they give you disks, they usually have some little thing thrown in. So this time it's the fact that it's a k. It's not really an actual value, right? Oh, giving away spoilers. Okay. So the radius of one of these disks, I'm going to draw one of these disks over here. The radius is just the height of the function. It's e to the 2x, right? So the area of one of these disks will be pi times e to the 2x squared. All right, and they want us to actually find the volume. So this is not just a write and do not evaluate. We're actually going to have to find the volume here. So let's do it. So we're going to integrate from 0 to k this area. So pull out the pi, and then we have e to the 2x squared dx. That is pi times the integral from 0 to k of e to the 4x dx, because power to a power you can multiply. Antiderivative of e to the 4x. When we take the derivative of that, it'll be by itself, but there'll be a 4 out front, so we have to anticipate that. So this is going to be pi times e to the 4x over 4 from 0 to k. So that is going to be pi times, let's see, e to the 4k over 4 minus e to the 0 over 4. E to the 0 is 1, so this is pi times e to the 4k over 4 minus 1/4. That's probably how I would leave it. Okay. If you want to distribute the pi, you could. I think they do, actually. Let's see. Yep, they do. So they have pi over 4 e to the 4k. That's this part right here. And they have minus pi over 4. Okay, but having it either way is just fine. I think for the next part of the problem, we'll probably distribute the pi anyway, but leaving it like this is just fine. So this gives the volume for any value k. The bigger k is, the bigger this is going to become. In fact, quite quickly it'll get big because it's exponential, and that'll give you the volume. All right, let's check out the next piece. So 4 points there. 1 for the integrand, so making sure that you have that squared, right, and the pi out front. 1 for the limits, so going from 0 to k. 1 for the antiderivative, so getting that pi over 4 e to the 4x. And then 1 point for getting the answer. 4 out of 4. Okay, so next the volume found in part B changes as k changes. If dk dt is 1/3, determine dv dt when k is 1/2. So, what do I know? Right, this is related rates problem. So we do know, what do I want to know, what do I need? So I know that dk dt is 1/3. So k is moving to the right. It's getting bigger, so this volume should be increasing. I want dv dt. So I need an equation that relates v and k. Okay, we have that. We just found it. The volume is, let's distribute the pi now, because I think that's going to make our lives a little easier. So the volume is pi e to the 4k over 4 minus pi over 4, was it? I think that's right. That's how they have it here. Yep. Okay. So now we just take the derivative. So dv dt. Now you're deriving with respect to time, so we have to make sure we use chain rule. The pi over 4 is going to disappear because it's a constant. So we'll have, let's see, pi over 4 times 4e to the 4k, right? Derivative of the baby function is 4, and then times dk dt. 4's cancel. Yay! Okay, so now we've thrown everything that we know. So dv dt is equal to pi e to the 4 times 1/2 times dk dt, which is 1/3. So that is pi e squared over 3. So that should be how the volume is changing. Pi e squared over 3. Let's see how we did. There it is. Awesome. So 1 point for chain rule, making sure you have that dk dt there, and then 1 point for getting the answer. Awesome. So that's the entirety of the problem. Did it in 8 minutes, so that's pretty good. And now we're going to kind of do all those extra little pieces that I added in. Let's see if we can do them using some disks, washers, and shells. Let's see what happens. So write but do not evaluate an integral expression to find the volume of the solid generated by revolving r around the line y equals e to the 2k. That is this line right here. Okay, so if we revolve around this line, let's see what we're going to look like. The curve will kind of go like that. So we kind of have this region right here, right? So we're going to have here our washers. Right? So we have an inside and an outside function. Inside radius, outside radius. So our outside radius the entire time is just e to the 2k. Right? Because that is the length, the distance from the line down to the axis. That doesn't change, right? From 0 to k, that outside radius is going to be the same the entire time. The inside radius is more interesting. Inside radius follows the function. So the entire distance from the top to the bottom is e to the 2k. The distance from the function to the bottom is e to the 2x. So this is going to be e to the 2k, that's a constant, minus e to the 2x. So by the time we get to the end, k and x are the same, so it ends up being 0, which makes sense because that whole is going to be completely diminished by the time I get that to the end. So the area of one of these washers, pi times the outside squared, so pi times e to the 2k squared, minus pi times the inside squared. Inside is e to the 2k minus e to the 2x squared. Okay. Usually we pull the pi out of that, and we're going to integrate from 0 to k. So pull the pi out, 0 to k, got to square them separately, right? So we have e to the 4k, that's the first part squared, minus, this part I'm going to leave in parentheses, so we have e to the 2k minus e to the 2x squared dx. Big parentheses around the whole thing, and that's our answer. So hopefully you were able to come up with that one. Now we start revolving around vertical lines. Yay! Okay, so we're going to revolve around the y-axis this time. So if we're revolving around the y-axis, our curve's going to look like that. So here's kind of the reflection around. So it looks like if we're going to do it in terms of x, which is how I would recommend doing it, because then we don't have to worry about functions changing, we're going to have shells. Okay, so if you take one of these sticks as you're integrating from 0 to k, it's going to create a shell like this. Radius is easy. Radius, when I'm at any x value here, is just going to be from this line to here, is just going to be x. I'm going around the axis, so it should be pretty easy there. And the height is just going to be e to the 2x. So the area of one of these shells, if you think about the rectangle, if you were to unwrap it, the length would be the circumference, so it's going to be 2 pi x times e to the 2x. So volume integral from 0 to k, 2 pi on the outside, x e to the 2x. dx. If you want to define that, you would have to use integration by parts. It would be a good candidate for a table, because we have a polynomial multiplied by a cyclic. Now, some of you may have said, wait, why don't I use y values on this? Well, you can. Let's give it a shot. So let's kind of draw that again. The trick with y values, though, is for a while, you're going to have just disks, right? So you have disks at the beginning. But then once you get to where the function comes into play, you're going to have washers. So it'll be washers as you get higher. Okay? So what you would have to do for this is first change to k. So y equals e to the 2x. Sorry, not to k, to y values. So that means that ln y is equal to 2x. So x is equal to ln y over 2. That's the curve right here, ln y over 2. So you could do here is you'd integrate from 0 to 1. You just have cylinder. It'd just be a cylinder, right, with a radius of k. So this radius initially is k. So you integrate from 0 to 1. Just when x is equal to k, so k dy, sorry, not k, we have to actually think about the disk. So the area of those disks is going to be pi k squared. So pull out pi k squared, I guess, if you want to, because k is a constant, dy. Then we add to that from 1 to e to the 2k, right, because that's the y value where we stop. So pi pulled out. Now for those washers, inside radius, outside radius. So the inside radius there is going to follow the function. The outside radius the entire time is going to be k, right? Because we're just following k all the way up. So the inside radius there is going to be just ln y over 2, right? Because that's the distance from the axis to the curve. Okay, so we're going to have pi times the outside squared, so k squared minus ln y over 2 squared dy. This is how it would be if you used y's. So if you wanted to pick a value of k and plug that into your calculator, plug this guy into your calculator too. I think this is a lot simpler using shells, but you can do it with y's as well. They should both give you the same answer for any value of k. All right, let's see what happens when we rotate around a different line. So now we're going to rotate around the line x equals -2. So -2 is like over here. Again, you could use washers with y and change the function as you go up. I'm going to do this with x's, so we kind of have a reflection over here. Okay, so if we do x's, we're going to have shells, because our stick here is parallel to our axis that we're rotating around. So we have shells like this. They're a little bit bigger than the last time. The radius now, so this is x. X is the distance from the axis to the point. And we're going to add to that 2. So this is x plus 2. And even though it's -2, we're adding. I know it's kind of weird. Okay, the height is still just e to the 2x. Okay, so the area of one of these things, 2 pi times x plus 2, that's the circumference, times the height, e to the 2x. So we integrate 0 to k, 2 pi on the outside, times x plus 2, e to the 2x. Again, could do this with parts for sure. Not too hard of an integral. Nice. All right, now we're going around the line k plus 3. So here's k plus 3, somewhere over here. Okay. This is probably the hardest shell method type problem that you could get. Okay. So if we take a point here, it's going to go to a point over here. So we're going to create these really big shells. All right. So here's our big shell. So the radius this time, let's see, well, the distance from here to here is x. So we're integrating from 0 to k. So every x value between 0 and k, we have to figure out the radius. So if x is the distance from here to here, the entire distance from here to here is k plus 3. I don't want the entire thing, though, right? I just want the k plus 3. I want to take away that x value. So your radius here, drawn on this side like I'm doing it here, so that's going to be k plus 3 minus x. Height still e to the 2x. So 2 pi integral 0 to k plus 3 minus x. That's our radius. As x increases, the radius is getting smaller and smaller. That makes sense because we're taking more away. Times e to the 2x dx. That's all there is to it. Hopefully you're getting better at doing these. After you do a bunch of them, finding these radii becomes easier and easier and easier. All right, was that the last one? It was. Finished in just over 15 minutes, even with 4 extra problems, and doing the one with the y's and the x's. Not too bad. Love you guys. That's why I'm here. Have an excellent day.